this gray box gives you the computational formulas for constructing any confidence interval. So the lower bound is right here. It's p hat minus z sub alpha over 2 times the standard error, which is the square root of p hat 1 minus p hat over n. And then the upper bound is p hat plus the critical value z sub alpha over 2 times the standard error again, the square root of p hat 1 minus p hat over n. Now the one thing I want to emphasize to, I guess a couple things I want to emphasize to you, the critical value, the z sub alpha over 2, the three primary ones we've given you right here. These are the three primary critical values for the three most popular levels of confidence, 90, 95, and 99%. The other thing I want to point out to you is that notice that for the standard error of p hat, the formula that we've been suggesting to you is that it's the square root of p 1 minus p over n, yet in the formula we're using p hat. The reason that we use p hat instead of p is because we don't know the population proportion p, so we use our point estimate, which is p hat. All right, so let's go ahead and construct a confidence interval for a population proportion. In a survey of 2019 adult Americans aged 18 years or older, 1,252 stated that they frequently worry about their financial situation. Obtain a 90% confidence interval for the proportion of adult Americans who frequently worry about their financial situation. All right, here's what we're going to have to do. And is we're going to first compute p hat. So here, p hat is the number in our survey who frequently worry about their financial situation, 1,252, divided by the number of adults in our survey, which is 2019. So we have 1,252 divided by 2019, and we're getting 0.620. So our point estimate is that 62% of adult Americans 18 or older frequently worry about their financial situation. Now, we're going to go ahead and construct the confidence interval. However, before we construct our confidence interval, we want to make sure that our model conditions for doing so are satisfied. Remember, we're using the normal model to construct our confidence interval, and therefore we have to make sure that the normal model is a good model for doing so. So these are the two conditions that must be satisfied. First, we need n times p hat times 1 minus p hat to be at least 10. So n, our sample size, is 2019. P hat is 0.620. And then we have 1 minus p hat, 1 minus 0.620. So if I do this computation on my calculator, I have 2019 times 0.62 times 0.38. I'm getting 475.7, which is definitely at least 10. That's our normality condition. And then we have an independence condition that my sample size can be no more than 5% of the population size. We don't give you the population size, capital N here, but we know our population is adult Americans. There's probably at least 200 million adult Americans in the US. So if I take 200 million times 5%, it's definitely bigger than my sample size of 2019. And so my independence requirement is satisfied as well. That means that I can use the normal model to construct my confidence interval. Here we go. We are doing a 90% confidence interval. And because we're doing a 90% confidence interval, that means my critical value is going to be 1.645. We know how to get that from StatCrunch, but it's also up here in this table. The critical value for a 90% confidence interval is 1.645. So now we just plug and chug into our formula. The lower bound is p hat minus your critical value times the standard error, the square root of p hat 1 minus p hat over n. P hat is 0.620 minus 1.645 times the square root of 0.620, 1 minus 0.620, all over n, which is 2019. I recommend that you compute that margin of error piece independent or first. So I'm going to do 0.62, multiply that by 0.38, divide that by 2019, take the square root, and then multiply that by 1.645. And I get, I'm going to write this down to the same number of decimal places. So that's going to be 0.018. And so now I do 0.62 minus 0.018, and I get 0.602. Now for the upper bound, that's just p hat plus my margin of error. And by the way, my margin of error is that 0.018. So I don't have to redo all these computations now. I can just do 0.620 plus 0.018, and I get 0.638. We would say we are 90% confident the proportion of adult Americans 18 years or older who frequently worry about their financial situation is between 0.602 and 0.638. Now, of course, we want to see, hey, how can I do this using StatCrunch? If you're going to use StatCrunch, and you're going to go stat, proportion stats, and then one sample. So let's go there. Get rid of that. So it's stat, proportion stats, one sample, and we have summarized data. Most of the problems that you work with are going to be summarized data. Raw data would be like we did with the tornadoes where we had a bunch of yeses and nos. So we have summarized data, and it says, hey, how many successes did you have? Here, a success is finding an individual who frequently worries about their financial situation. That's 1,252. And then number of observations, that was 2019. You check the confidence interval radio button, and then down here you enter in your level of confidence. We're doing a 90% level of confidence. The method is always going to be the standard walled method, standard meaning using the standard normal curve.
Gotcha.
And then we click compute. And there you can see the lower limit is 0.602 and the upper limit is 0.638, just like we got when we did this by hand.
StatCrunch is always lovely.
Yes. And so let me put down the interpretation. I'm just gonna move this part C someplace else. So it's because this is the key here, is the computer can give you the results, but you're going to have to still do the computation. We are 90% confident the proportion of adult Americans who frequently worry about their financial situation is between 0.602 and 0.638.
So you're saying we have to write that out?
Yes, you're going to have to write this out.
Okay.
So that part C there that I crossed out says, what if we increase the level of confidence to, well, I guess it's right here actually. I took over all of that. Part B, I should say, says, hey, what if we increase the level of confidence to 95%? What happens to our confidence interval? Now, before we actually do this, think about it. If you're going to be more confident that your interval captures the population proportion, do you think your interval will be wider or narrower? Well, here, I'm going to ask a different question. Would you have more confidence the average age of a JJC student is between 25 and 35 years old, or between 20 and 40 years old?
Well, 20 and 40 years old.
Yeah, why is that?
It's a wider margin.
A wider interval. So flipping that, if we increase our level of confidence that the interval captures, what do you think it's going to do to the interval?
It's going to widen it then.
It'll make it wider. So then I have a better chance of capturing the unknown parameter if it's wider. It's a bigger net, so to speak.
So at a very low confidence, the upper and lower limit would be very close then.
Yes.
Okay.
Yeah. Right? So let's see if that plays out. Let's change my level of confidence to 0.95. And when I change my level of confidence to 0.95, 95% confidence interval, notice the lower limit is 0.598 and the upper limit is
0.641.
Yeah, 0.641. And so here we can say we are 95% confident the proportion of adults who worry about their financial situation is between 0.598 and 0.641. And so, yeah, the interval got wider as I increased my level of confidence.
But even with the highest confidence, there has to be a limit, right? Like a full limit.
Yeah, I mean, you can't. There's a limit to how high you can set your level of confidence, right? I mean, I want to be 99.99% confident. I've never done this. Let's see what happens.
That's pretty confident.
Yeah, and even there, your lower and upper limits aren't that far apart.
Right.
That's primarily because of the fact that my sample size is actually pretty darn big here, right? Because if you think about this formula, and this is why showing how to do this by hand is important, you can see the margin of error is impacted by two things. It's impacted by the critical value, which is really your level of confidence, impacts that Z value. And the other thing that it can impact your margin of error is the sample size.
Right.
And if I make N get bigger and bigger and bigger, this whole fraction gets smaller and smaller and smaller, which makes my margin of error smaller. Right? So I can get more precision in my interval also by increasing my sample size.
Gotcha.
Which should make sense. That's the law of large numbers once again. If I survey more folks, I should feel more confident in my estimates. Right? Mm-hmm. You're less likely to vary from your goal. And that's kind of like that's what's happening in letter D here. Let's say we increase our sample size fourfold to 8,076. So I'm literally quadrupling my sample size to 8,076 and also increasing my number of successes, folks that are financially worried, to 5,008. So if I look at that, this is 5,008 successes now out of 8,076 folks surveyed. And I do another let's say I do my 90% confidence interval. This is what I get. And let's compare it to the earlier scenario. Remember I said that the margin of, So my p hat is still 0.620, right? So p hat minus the margin of error is going to give me my lower bound. So if I do 0.620 minus my margin of error, and I have a lower limit of 0.611, you see that right here? The margin of error is really 0.620 minus 0.611, which is, so that's 0.009. Whereas when my sample size was 2019, my margin of error was 0.018. When I quadruple my sample size, the margin of error is 0.009.
Yep.
So in order to cut your margin of error in half, you have to quadruple your sample size.
Jeez.
Right? And so getting more accuracy through the sample size is pretty expensive in terms of how many folks have to be surveyed.
Right.
Is the moral of the story there. Okay.
But it does lead to the more concise results, right?
More precise, not concise. Precise.
Yeah, precise,
results.
right?
Yeah. Exactly.